All right, shall we get started? A rhetorical question, really. We shall get started. So we shall get started and finished with the determinants, or not completely finished. I mean, finished with the basic properties of determinants, and then we will be using them like from now on, pretty much all the time. As I said, determinant will be critical in defining what are eigenvalues and eigenvectors, and everything else then follows from that. So let me just quickly recap, because I checked and I had only one view on the video I recorded on Monday, so I lost any hopes that anybody re-watched that. Though I think it was quite a lot of information at one time. I don't know, or was it easy to follow? I don't know. I mean, if I didn't know it before, I probably would not remember all of that. So let me recap quickly. It's not such a big deal. So determinant is a function of a square matrix, and we are dealing just with real matrices. They always have to be squared by n. And it assigns the matrix just a scalar, just a real number. And we denote it either like this or just with these vertical bars. And we define determinant using these three properties. We said that the determinant is a mapping that satisfies these three rules. So let me restate them, because we will need them. I will need to refer to them again today. So the first one is simple. The determinant of identity is just 1. When you flip, the second rule is if you flip two rows, if you exchange or switch two rows or equivalently two columns, the sign of the determinant changes. And the third one is that the determinant is linear with respect to every row or column, but this linear, you have to be very careful about it. It doesn't mean that this mapping would be linear, that's what I was explaining, but it means that the determinant is linear if only the one row changes or one column changes and everything else is held fixed. So what that means, if I expand one row like this one into sum of scalar multiples of two different rows, then I can write it as a sum of two determinants, and the scalars multiply out. So this is what is meant by the linearity. So these are the three defining rules of a determinant, and then we had a bunch of rules which follow from this logically. This is the definition, and then we have lots of derived rules. And what I'm trying to do right now is to build up to essentially to a formula, how to compute determinant for an arbitrary matrix, and how to derive the formula for determinant. So those are actually two different things, right? The formula, as I was explaining on Monday, is not really useful for not super useful in computing the determinant. If you really want to compute a determinant, it's better to first transform the matrix to reduced row echelon form, or do some transformation like that and compute the determinant in that form. So this, let me also quickly recap. This is what we will still need. So let me remind that this is what we had the last time, but let me just remind that. So this is sort of the strategy. We want to transform the matrix by elementary row transformation, just like we were doing in the first part of the course, to transform it into a simple matrix, typically into a diagonal matrix, ideally. And what we already shown the last time is that the determinant of an elementary row transformation on the matrix A can be written like this. That we have these, let me remind this too, what are these elementary transformations? So these elementary transformations are just matrix representations of the transformations I discussed in these rules, right? The first one is swapping rows, right? This is a matrix way how I tell how I say in matrix language swap rows, right? This one was a matrix way of saying multiply a row by a scalar, right? So this is one part of the linearity, and the third one is also another part of the linearity. This means add a multiple of one row to another one. And what we have shown that some of the derived properties are, that's what we discussed on Monday, is that if we do this transformation, the determinant doesn't change. If we add a multiple of one row to another row, the determinant stays the same. If we do this, then the determinant is scaled by alpha. And if we do this, the sign of the determinant flips. That's exactly the defining rule number 2, right? And we can, of course, easily compute determinants of these elementary matrices, right? Again, just directly from the rules, right? This is just a swap of 2 rows from the identity. We know that the determinant of identity is 1. And by the rule number 2, this has to be -1, right? Because there is one flip. Here, just by applying the linearity, the determinant of this is alpha. And this is just a tiny bit more complicated, but that's what we showed before, that this means the determinant doesn't change. The determinant of this is 1, just like the determinant of identity. So from this, we were able to prove this property, that if you have an elementary matrix, then it doesn't matter if we first perform the operation, do E times A, and then take the determinant, or if we first do the determinants and then multiply them as real numbers. So here, this like invisible dot is just like a real number multiplication, and here this is like a matrix multiplication. Yeah, it's pretty good resolution. You can see a tiny dot there. So, did I cover this? I can't remember now. Let me go through it again. Anyway. So if I have, I think I did. I think if I have, I think I did. I think if I have so the point is, if I have invertible matrix, I can bring it to a reduced row echelon form, which is just the identity, by a sequence of elementary row transformations. And if I take determinant of both sides, obviously if the matrices are the same, then their determinants must be the same as well. And by this rule, I can just isolate these individual determinants of the elementary row transformation matrices. This is just applying this rule. This is what I was explaining before. That like first I take the E1 out of it, then the E2, and so on. It's just like iteratively applying this rule over and over again. And then because the elementary matrices are invertible, then I can invert this whole thing, and I see that the determinant of A is just the product of the inverses of the determinants of the elementary row transformations. So this tells me how can I compute the determinant of an invertible matrix. So that's actually quite useful thing. The determinants of the elementary matrices I know, right? So all I need is to reduce the matrix to a reduced row echelon form, get these transformation matrices, find their determinants, and I'm done. This is one practical way how to compute the determinant. Like computationally, what would be the complexity of this if it was like an algorithm? If I wanted like an algorithm to compute determinant. So the formula we were discussing before is that it has n factorial terms, and I will show you hopefully today how the formula actually looks like. So for n by n matrix, n factorial terms is a lot, right? For like 10 by 10, that's already like 3.6 million or something crazy like that, right? It just grows exponentially, like even super exponentially. It grows like crazy. But the complexity of this algorithm is more reasonable, right? What is the cost of transforming matrix to reduced row echelon if it's an n by n matrix? Almost. It's n cubed, right? This O n cubed. That would be the complexity of this algorithm too, because all I need, so this, the bottleneck there would be the conversion to the reduced row echelon form. So a related result to this is this one, which is sort of trivial, but it's good to realize this, that the determinant of a matrix which is a diagonal matrix is just the product of the diagonal entries. So if I have a matrix like this, and everywhere here are zeros, so this void means zeros, really, but let me just write that it's really zeros. And this really follows directly from the linearity of the determinant, right? Because each of these rows I can write as the scalar times 1, right? So I convert it to like multiplication of all these scalars times the determinant of identity, which is 1. So it's just their product, right? If there are some negative ones, that's fine. It still works. Okay, so let's look. So this is essentially the basics, and let's look at the next stuff. So this is this is actually interesting. So this eventually will lead us to the statement that the determinant of the matrix is 0 if and only if the matrix is singular. But let's start by these observations. So first we observe absolute value of the determinant is equal to the absolute value of the product of its pivot elements. So it's almost the same up to a sign. That's what I mean by this absolute value here. So let's first consider invertible matrix. Then in the second slide we will consider a non-invertible singular matrix. So if it's invertible, then all of its pivot elements are not 0, right? That's a mistake. Are non-0, right? And by doing the elementary row transformations, we type 1 and type 3. Oh, right. The type 2 was the multiplying row by a scalar, so that's what we don't need here. We only need the type 1 and type 3. So the type 1 was exchanging rows, and the type 3 was, oh, it's actually written here, interchanging rows and adding a multiple of one row to another. The interchanging rows was type 1, and adding multiple of one row to another was type 3. And the type 3 doesn't do anything to the determinant, right? Adding a multiple of one row to another row just leaves the determinant as it is. And the type 1 flips the sign. It multiplies it by -1. That's what I mean by flipping the sign. So if it's invertible, then I can reduce it, the reduced row echelon, not the reduced, the row echelon form, or like special type of row echelon. I can bring it to a form that everywhere are zeros, except on the diagonal. And of course, if I do this, then the determinant of this entire thing, the absolute value, is the determinant of this diagonal matrix, which is just the product of the diagonal elements. The only catch here is that if I had to do some row swaps, then the sign might have changed. But that will not matter. Let's look at the other case. So this was essentially showing the statement for the special case where A was invertible. Now we need to think about the case that if A is not invertible, if A is singular. So what do we know about a singular matrix? So we know that it can be brought to this elementary form where at least one of the pivots will be 0. So I think now it's correct here. At least one of its pivots is 0, yes. So then it means that the product of the pivots will be 0, right? Because we have there 1, 0, so it will turn everything 0. So in this case, actually, the absolute value doesn't even matter because at the end of the day, we have the product of all the pivots, which is 0. So again, the story is the same. By applying elementary row transformation, except for the scaling, the type 1 means also scaling, but only by -1, so it's only changing the sign. Then I reduce the matrix to this diagonal form, and the determinants have to be the same of these two matrices. And the determinant of this one is 0 because I just multiply all these diagonal elements and I get 0. So this shows the very nice property of the determinant. So essentially in both cases, the determinant and the absolute value of the determinant ended up being just the product of the pivot elements. So from this we can conclude that it's indeed true that if the matrix is invertible, then the determinant is non-zero, and if the matrix is single, then the determinant is 0. This if means if and only if. I don't know if you have seen that. Probably yes. I sometimes also write it write it like this, like two-sided implication. I could also like write it like this. The determinant A is 0 if and only if A is singular. So this is nice, right? This is like a very convenient tool, essentially. How can we check if a matrix is singular? So the determinant really contains some useful information about the matrix. This is like one tangible piece of that information. It contains even more, and I will later explain how the determinant relates to like a volume or hypervolume or area, depending on the dimension we are at. But this is already a useful result. So remember that the determinant is 0 if and only if the matrix is singular. And we are talking still just about square matrices. All this is just about square matrices. Yeah?
And the determinant is always the product of all the given elements in reduced row echelon form?
Right, up to the sign, yeah. Right. If you keep track of the sign, then that's how you can compute the determinant. Yes.
Is that the way it's typically computed?
That's a good question. That's one way how it can be computed in n cubed.
Is n cubed would be less than n factorial, right?
Of course, way less. So this is like a much better idea how to compute a determinant. In practice, I don't know if determinant really is computed all that much in practice. These formulas are useful, but usually only for very small matrices. I have seen this used like in like graphics libraries when you want to like invert 2x2 or 3x3 or 4x4 matrices. Then you like use the determinant formula. But when you need to do like some sort of like hardcore linear algebra, by hardcore I mean like thousands, tens of thousands, millions of variables, I have rarely seen the determinant being used explicitly. It's more like a tool from which we will define the other properties like eigenvalues and eigenvectors. But then there are specialized algorithms for eigenvalues and eigenvectors which don't work by computing the determinant first. But like this is useful as it is for small matrices. I have seen it used, and these formulas for determinants, they are there. Because then I don't think I will discuss that. But like you can also use the determinant to form formulas for like inverse matrix and for solving linear system. But again, I think it's only or mostly it's useful for small matrices. Okay. Yeah, here is one rule which is very important. The product rule of a determinant, which is something definitely worth remembering. For any matrices, I mean, they have to be square, of course, but for absolutely any matrices, the determinant of the product of the matrices is equal to the product of the determinants. So far we have shown this only for the elementary matrices, right? When the A was an elementary transformation matrix. For this case, we have already shown this because the elementary matrices are so simple, but it turns out it actually is true for arbitrary square matrices, A and B. And this rule is like really useful. That's definitely worth remembering. So let's take a look why this rule is true. And we will consider two cases. So the first case where either A or B are singular, then the product also has to be singular. And obviously determinant of a single matrix is 0, right? So if this is 0, then if either one of them is singular, then the determinant will be 0. So this equality reduces to 0 equals 0. So that's trivial. The only thing, can you give me a reason why if A or B is singular, the product will be also a singular matrix? So let's assume, to be concrete, if A is singular, why the product AB will also have to be singular matrix? Could it not happen that I could find some funny B that I would get like a regular matrix? What do you think? This would have been like another nice like midtermy question. I think it's slightly tricky, not super tricky, but slightly tricky. Again, the question is, if I have A singular, why the product of A and B, where B is some matrix, maybe singular, maybe not, why the product AB is also a singular matrix? In other words, it's saying that I cannot fix the non-invertibility by multiplying it with another matrix. Yeah, also, I think it's not. So here is one simple reason. So let's look at the column space of A. So if I assume that A is singular, it's square, right? We are only dealing with square matrices. So it means that the dimension of the column space is strictly less than n, right? But what is AB? In particular, what is the column space of AB? So what does the multiplication of B do? The B makes only linear combinations of columns of A, right? Every column of the product AB is a linear combination of columns of A, right? So there is no way the B could create something, some vector which was not already in the column space of of A. So that means that the column space of AB is a subset of the column space of A. That means that the dimension of the column space of AB must be also strictly less than n. It actually has to be less than or equal than the dimension of the column space of A, which is less than n, right? So definitely if A is singular, then AB is singular, and that's why this formula is true in this case. If B was singular, then you can construct the same argument by looking at the row space, right? Because what AB then does, A then means take linear combinations of the rows of B, right? And the argument just works the same way. Or I could transpose everything and essentially refer to the same argument. Is that clear? More or less? Okay, so that's like the odd case. That's the corner case first, and now the regular case. So I'm proving this identity. Actually, it's so important that I will like under frame it. So in the case that both of them are invertible, so if either of them was not invertible, then the first case applies, right? I just multiply by 0. I have to get 0 here. Fine. If they are both invertible, then I can write A as a product of elementary matrices, right? Type 1, type 2, type 3. And for elementary matrices, the E's, so A I will write as E1, E2 to EK. And for elementary matrices, I already know that this formula is true, right? That every elementary matrix corresponds to some transformation of the remaining matrix. And I can just pull out the determinant there. That corresponds to multiplying the determinant of the remaining matrix with the determinant of the first matrix. So I can write it out as the product of the individual determinants there. But now I can look at the product AB, and I know that A is the product of these elementary matrices, and I can apply again the same argument. Doesn't really matter what all is here, right? I can just one by one pull out the determinants of the individual matrices. But then this thing is the same as this thing, right? So this is just determinant A. So this is what I get here, and indeed I'll see that determinant AB is the same as determinant A times determinant B. So the way this proof works is essentially refers to the fact that this is true for elementary transformation matrices, and in the invertible case, I can just write A as a product of elementary row transformation matrices, and that's why it works. If A is not invertible, then this first case holds, and as 0 is 0, and it also works. So it's a very, very useful identity. It's true no matter what. The only thing you need to be careful is that they are square matrices. And once you remember this, like I guess the previous slides were only like complicated because like we had to derive this, right, rather than like give it as a dogma. But once you remember this, then like all the things come very, very trivially. Once you know that you can, once you know this, then all you need to do to compute determinant is to reduce it to the elementary row transformations, apply this rule, and you know how to compute determinant, right? So if I gave you a task to compute determinant of an arbitrary matrix, you know how to do that. All you would need to remember is this rule. So it's sort of nice. So it's definitely worth remembering. So there are some cool corollary. How do I pronounce this? Consequences, corollary. Say it again.
Corollary.
Corollary.
Yeah.
You know what I mean, right? There are some important statements that follow from it. One of them is the inverse rule. The determinant of inverse matrix is 1 over determinant of the original matrix. It's sort of simple, but let's take a look. Why is that? It follows from this rule. So that's our corollary, whatever that is. So the determinant of A inverse. So on one hand, this is determinant identity, right? Which has to be 1. That's our rule number 1. On the other hand, I now have this product rule. So this is determinant A and determinant A inverse. So obviously, if this is 1, that means that determinant A inverse is 1. That means the determinant A inverse is just 1 divided by determinant of A. And you can notice that if A happens to be singular, if A is not invertible, then this is nicely not defined. Sort of makes sense, because then the determinant is 0, and this formula would ask me to divide by 0, so I cannot do that, right? So it's only defined when the inversion is defined, which is sort of nice. It's like compatible with the definitions. The other thing that follows from this is that the determinant of a transpose of a matrix is the same as the determinant of not transposing the matrix, which is nice. In a determinant, you don't have to worry about transposition. Good thing to have. So why is this true? Because again, so if A was singular, then this is 0, right? Doesn't matter if I transpose a singular matrix, I still have a singular matrix, so it's still 0. If it's not singular, I can again write it. I guess maybe this would work even for a single matrix. So either way, I can write A as a product of the elementary row transformations, and then I know that the determinant of transposed elementary matrices is the same. That's sort of trivial to see just by looking at the elementary row transformation matrices, right? Some of them are already symmetric, so in some of them the multiply row by a scalar transposition doesn't do anything, and for the ones where it actually does something, you see that the determinant doesn't depend on whether it's the matrix or its transpose. So from that, obviously AT is what? You tell me that. If A is a product of E1 to En, AT will be what? Well, that's the slight trick, right? It will be, but it will be flipped, right? It will go the other way around, because always remember this rule: AB transpose is B transpose A transpose, right? And here I'm just applying it like peeling off the products one by one. So the determinant of A is the determinant of all these individual, or let's do AT. It's the determinant of these guys, which I can now split, right, to ENT times, because I have my product rule. Oh, sorry, I'm writing a nonsense. I'm trying to speak and write at the same time, which is not working. So this is my product rule. Then I can take the transpositions away, and let's do it one by one nicely, because this is true for the elementary matrices. And then of course this is just a multiplication, so it's commutative, so I can flip the order. then I can all bring it back. I'm like doing it like very slowly. I guess I could also make it faster, which is just determinant of A. Right, so this is showing that the determinant of transpose of A is the same as determinant of A. So the consequence of this is that all the determinant rules, whenever there are rows involved, you can also replace, you can do search and replace on the slide. Wherever there are rows, you can also equivalently formulate it with columns, because the AT exchanges the role of rows and columns, but the determinant doesn't change. So the determinant doesn't care if you are doing operations on rows or on columns, because it doesn't care if it's looking at matrix A or A transpose. Okay? Okay. So next I would like to show you the big formula. From this we can sort of derive the general formula for determinants. I don't have slides for that, but I will try to explain it just with a pen and paper. It's not that bad. And actually, one thing I still owe you is to I started on Monday by giving the formulas for the determinant of 2x2 matrices, and 1x1 matrices, and 3x3 matrices, right? But I still need to show that they are compatible with the rules, that these definitions are actually equivalent. So this is what I would like to explain now. So we have to start by reiterating what are permutations and permutation matrices. Do you know what is a permutation? The general definition of a permutation? Permutation P is a mapping from, let's say, on set of numbers from 1 to n, which is a function from a set of numbers from 1 to n to 1 to n, such that P is bijective. So what it means is that, like for example, if n was 3, I can say that P1 has to map somewhere, so for example to 2, P2 has to map somewhere else, and P3 is also something. So this would be an example of a permutation on like three elements. Did you have that somewhere? Does it ring some bell, permutations? What I was discussing here earlier was that we can represent permutations using permutation matrices. In this case, it would be a 3x3 matrix, which would look like this. And the point is really still the same. I'll try to squeeze it here. If I take some vector ABC, what the permutation matrix does, look at it. Here I get B, here I get A, here I get C, right? So what it really does, it takes the first element and, or now on the first coordinate of the result is the second element. The second coordinate of the result is the first element, and the third is the third. That goes unchanged. So that's exactly what the matrix does. So determinants of permutation. So how we define permutation matrices is that they are binary matrices. They only have 0 and 1s. And in every row and column, there is exactly 1, 1. This is how we previously defined permutation matrices. So permutation matrices are one way how to represent permutations, which are mappings from some set to the same set, which is bijective. Oh yeah, and there is of course how many permutations do I have on a set of n elements? N factorial, exactly. So does it ring a bell? See, permutations are sort of closely related to determinant. So the determinant of permutation matrices is very simple to compute, right? If I have, for example, let's do a 4x4 case. What would be the determinant of this matrix? What do you think? So it's just like identity, except that not, yeah?
Be -1.
That's true, yeah, that's -1, right? So any permutation I can construct from the identity permutation by flipping pairs, right? So, or in the language of matrices, any permutation matrix I can construct from the identity matrix by flipping rows or equivalently columns. And what does it mean for the determinant? We know that the flip of rows or columns changes the sign. It multiplies the determinant by -1. So in other words, if I make an odd number of row exchanges, I get -1. If I make an even number of row exchanges, I get +1. So the determinant of a permutation matrix is as simple as that. For arbitrary permutation, I need to look how many exchanges that I need to do. And this will tell me whether the determinant is +1 or -1. There's no other choices. Okay. So this is like a very quick primer to permutations. You could be studying permutations more. There's like lots of group structure in permutations and so on. But for the determinant, we just need this basic knowledge. So let's now revisit the determinant formula for a 2x2 matrix. So I want to now compute the determinant of a general 2x2 matrix. And this is where the determinant formulas are like really most important for small matrices. So I started on Monday by like saying how the formula looks like, and you probably still remember it, but now we want to derive it from the 3 rules, right? Now we want to show that these things, that I was not really telling you crap, that this is really derivable from the determinant properties, from the defining determinant properties. So how do we do that? So we take a look at the first row. So the first row is a vector AB, and I can certainly write this as a sum of these 2 vectors, row vectors, A0 and 0B, right? And now by the linearity property of determinant, this means that the determinant of ABCD, of the general 2x2 matrix, it splits into these 2 determinants, 0B and CD, right? That's because the first row splits into 2 vectors, A0 and 0B. So the determinant splits into 2 easier determinants. Yep. Now guess what? I can do the same thing on the second row, right? So I guess I wouldn't even need to write that, and now both of them, or every single one of them, I can split again, right? So the splitting of the first one gives me this, A0, C0 plus A0, this I just copy, and 0D. So this is I took the first one and I split it by splitting the second row. Did I do something wrong? What should be? I think this is okay. I mean, I'm not finished yet. What follows here is the splitting of the second one. So here is the 0B, and here is again C0, and here is 0B and 0D. So this is now the now the equality is true, right? Here I was not finished yet. So this is splitting the first one. This is splitting the second one. And this is just applying the linearity rule of the determinant that I can mess with. If the row split, then the determinant split. That's the rule number 3. That's this right here. That's exactly this rule, what I applied there. So then remember, we have shown that if there is a column or row of all zeros, then the determinant is 0. So the determinants of these matrices are 0, so they just fall out. Because there is a column of all zeros, and there is also a column of all zeros, so these guys are out of it. And the next thing we can apply is again the linearity, this time by extracting the scalar multiplication. So I can extract the A times D, and what remains here is just the determinant of the identity matrix. And here I get, so this was this one, and this one gives me BC times the determinant of this matrix. Everybody agrees? This is again just applying this rule, applying the other part of the rule. This is just pulling out a scalar. And I pulled out two scalars at the same time. Both A and D. I could do it like in steps, but I guess I don't want to underestimate you. So this is a determinant of identity. So this is 1. And this is identity except for one row swap. So this is -1, right? So this gives me AD minus BC. And this is really the determinant of an arbitrary 2x2 matrix, now derived from the rules. So you can now see that this formula is not really that like some dogma, it really follows from the rules. Okay? Now what would we do for a 3x3 matrix? There it starts being a little bit more challenging. A, B, C, D, E, F, G, H, I. Determinant of this. Well, the idea is the same, right? I can again take the first, let me put it like here, I can take A, B, C and split it in 3. I can split it in A0, 0 plus 0, B0 plus 0, 0, C, right? And I can take the second row and do the same thing, and the third row and do the same thing. So here I would end up with 27 terms, right? 3 by 3 by 3. So I don't want to write all 27 terms, and I notice that I can immediately discard the ones that have like a whole column or whole row full of zeros. So all the terms that will actually be non-zeros there are such that the non-zero terms are unique in every row and every column. So if I do the expansion, like if you are really into it, you can actually do it completely in the discard, but I'm not writing the zeros there because it would be a lot of writing. But whatever the void is just 0. DBI plus GEC. So everywhere else is zeros. So really those are the only ones that survive, that don't leave any zero column or row. And I can again pull out these scalars and get this BGF 111 plus DHC 111 plus AHF 1 CBI 1 plus GEC 111. So those are just determinants of permutation matrices here, and these are just scalars. So now I have 6 terms, right? It's not a coincidence that this is exactly the number of permutations on a 3-element set. This was the number of permutations on a 2-element set. And it turns out that the determinants of these matrices are 1, because that's an even number of row exchanges. Here would be 0, and here we get it with 2, I think. And this would be an odd number of row exchanges. So the determinant here is -1. So this is the formula for a determinant of a 3x3 matrix. And I can now, by essentially doing this argument for a general matrix, I can write down, so if A is n by n matrix, I can write down, this is called the big formula. This is the formula for determinant of a general matrix. So it sums over all permutations. So I will denote this as the set of all permutations on an n element set. And it's a determinant of the permutation. So that's either plus or -1. times this. A2, B2, and so on, times A3, AN, PN. This is N. Okay, I will write it again. AN, B. Oh no. AN, B, N. So what this means is taking the first row of the matrix and then the element where the permutation sends the first one. That was this. Right? So this is the action of the permutation on my indices 1, 2, 3, 4 up to n. So this is the big formula, or the explicit formula for how to compute the determinant of an n by n matrix. It goes over all permutations, so it has n factorial terms. And for each permutation, I take its determinant, which is either plus or minus 1, depending whether it's odd permutation or even permutation. And then I take the elements of the matrix corresponding to the permutation. So for every row, I look where the permutation sends the row index, and that's the corresponding column. Okay, did it make sense? You probably will never want to really use this formula, but it's sort of good to know that there is a formula and that it looks like this, that it has n factorial terms. Obviously for computations you would never want to use it, right? It's always much more efficient to like convert it to reduced row echelon and compute the determinant of it. But it sort of has some cool combinatorial properties. And the other thing I wanted to mention, but I think I'll have to mention it on Friday because it takes some explaining, is how exactly is determinant related to area in 2D, volume in 3D, and like hypervolumes in like higher dimensions. So I guess I will explain that on Friday then. Okay, any questions? Nope. I guess I will see you on Friday then.